All right, so last night's assignment was just started you off with straight up Pythagoras. And it's hard when we take you back to Pythagoras, which you probably forgot that you knew how to do it, because you had all those other theorems in your head, whether it was the altitude drawn to the right angle, to the hypotenuse of a right triangle, or whether it was your special right triangles. A, B, and C are none of these. They're not special. They're not an altitude drawn to the hypotenuse. They're just straight up Pythagoras. So when you look at the values, so we get into that radical math. The square root of anything squared is that thing. Hopefully the more you're doing this, the more it's sticking with you. Number B, in letter B, instead of solving for x, because this isn't given to me as a right angle. Like nobody said that this angle was a right angle. So I can't call x a hypotenuse. I can't do any right triangle math with this big triangle because nobody gave me a right angle. And that's the one thing that becomes so super important. When you approach every single one of these triangles, your first step is just, wait, what am I looking at? Do I have a right angle? If you don't have a right angle, you can't use Pythagoras. You can't use the altitude to the hypotenuse of a right triangle. You can't use your special right triangles. So for this one, I get this right angle here. I get these two congruent angles, which means that these are two congruent sides. But it's this side that I need to solve for because I have my C and my B. So I'm going to solve for my A. Once I get my A, I'm going to double it to get my X. That was tricky. For letter C, the biggest mistake is kids think that X is the hypotenuse. It's not. 9 is your hypotenuse because it's the side opposite the right angle. So setting up the Pythagorean theorem on this one, definitely tricky. Because chances are you thought the x was the hypotenuse. So if you screwed up here, that was probably your mistake. If you screwed up here, you probably assumed that was a right angle when it wasn't. And maybe if you messed up here, you got tangled up in the radicals. Would you please turn to your partners and say which one of these you found the trickiest on your mark and set, go. All right, let's check out the next two problems. This is strictly my Pythagorean converse. And if you'll notice, I'm always writing c squared compared to a squared and b squared. And the hardest part about each of these is to determine which side is the largest. Now you can see here, I always end up circling my largest side. That helps me. When I'm dealing with a triangle, somebody said to me, how do you know which one is the hypotenuse? Your hypotenuse is the largest side. And you don't have to pull out a calculator. You could use estimating. Let's do it. So the square root of 17 is going to be a little bit more than the square root of 16. The square root of 16 is 4. So 2 times 4 is 8-ish. Right? So 6 times the square root of 2, the square root of 2 is more than 1, right? But less than 2. So that's going to be 6 and stuff. This one maybe is hard to tell which one is the biggest side. So maybe you needed to use a calculator to compare those values. When I compare those values, I've got 2 times the square root of 17, and I've got 6 times the square root of 2. Using the calculator for this one is a better choice because it can tell you which one's your biggest. That's how you know that this is going to be your c squared that you're comparing. So for A, I got obtuse, B right, C obtuse, D right. For 5, I got right, obtuse, and acute. Anybody want to talk about any of those questions, comments, concerns, worries, complaints? All right, 6 and 7 were all about the altitude to the hypotenuse. And you had to carefully read what it is that we're asking you to find. The altitude to the hypotenuse of a right triangle divides it into two segments. It says sketch the triangle and determine what is the length of the short leg of the original triangle. So that x is a geometric mean between the piece that is touching and the whole. I think I was listening to Sumner when he was doing this one. He's like, what? It works out. Things never work out evenly. Was that this one you were talking about?
I think it might have been
One of the other ones, maybe?
it was 10 and 12 under that.
Number 7, the hypotenuse of a right triangle is 15. The long leg is 9. What is the length of the altitude to the hypotenuse? So I sketched that triangle, and I came up with my own x values to solve. This I called x. So I went ahead and said, okay, 9 is the geometric mean between the piece that is touching and the hole. So once I got x, I subtracted that from 15, and I got a. Once I got, I got 9.6, and then I was able to solve for a, because a is the geometric mean between these two pieces of the hypotenuse. And that's how I got 7.2 for a. Questions on these? What's on the back here are just 6 real quick application problems for Pythagoras. We want to make sure that you're doing 2 things. Number 1, identifying what is the hypotenuse and making sure your hypotenuse squared is set equal to a squared plus b squared. And we want to make sure that in a real world problem that you're using units. Now, my rule of thumb is if you're in a real world problem, I'm okay with the decimal value. If you went ahead and simplified the square root of 80 to 4 roots of 5, that's fine. But in a practical situation, if somebody said to you, hey, how high is this ramp? And you went, that's 4 roots of 5, somebody might look at you going, what does that mean? So they would rather have that information given to them in decimal form. Did you catch your special right triangle here? Anybody do this one super fast? This is an isosceles. This is an isosceles 45, 45, 90 triangle. So if you've got 25, 25, this side length here is just 25 roots of 2. Again, if somebody's building the roof on your house and you tell them, I think I need my house to be 25 square roots of 2 wide, they're going to look at you like you're crazy. So in this circumstance, having it as the decimal is maybe the better choice. Any questions on these 6? Now come the fun ones. Would you please, with your group mates, talk about the fun ones, talk about how you approached solving them and whether or not you were successful on your market set talk. So we have our 45, 45, 90 triangle, and that pattern repeats, and it repeats in a spiral. You can see it growing around. Our 30, 60, 90 triangle, for me, I started up here with the 4, and I did half of 4 was 2. This is 2 roots of 3, which makes this root 3, which makes this 3, which makes this 1.5, which makes this 1.5 root 3. This is half of that. And then this times root 3 gives me 0.75 root 3 times root 3. So 75 hundredths times 3 is 2.25. I thought that was a cool one. This one's wackadoo because it mixes your 30, 60, 90s with your 45, 45. So that one was fun to find. This is all application of our special right triangles. If you skipped it or said no thank you, give yourself another shot. See if you can go back and figure it out. It's not that hard. So this one, we only get to use one special right triangle here. And then we need to jump into using Pythagoras. 1 squared plus root 2 squared equals 3 squared, or root 3 squared. And then this plus this equals that squared, that plus that, and you get root 5 as your x. So your special right triangle was only applicable for this one. Sound okay? Yes. All right, so today's warm-up, I'd like you to zip through and solve these 4 special right triangles. And I want you and your partners to have a conversation about why can't I solve for the height of the flagpole in the diagram? Your mark is set, talk. All right, so hopefully when you look at A, B, C, and D, those are quick and easy solves for you. Check your answers with mine. 8 is my short leg, so my hypotenuse is twice that at 16, and my long leg is at 8 roots of 3. It's a 30, 60, 90 triangle, so that's the one with the root 3. In letter B, it's a 45, 45, 90, the isosceles right triangle, and I know that 10 is my leg times the square root of 2. So if you say that out loud, join me. 10 is my side length times root 2. By saying that, it's what helps you set up the equation. 10 is side length times root 2. Then all you got to do is solve for your side length. Your side length is going to be 10 over the square root of 2. Hopefully someday you can leave your answer like that. But for now, we need to rationalize it by getting that radical out of the denominator. So we end up with 10 roots of 2 over 2, and that simplifies to 5 roots of 2. So 5 roots of 2 is both sides, x and y. 8 is short leg times root 3. Say it with me. 8 is short leg times the square root of 3. So when I divide each side by the square root of 3, I end up again with a radical in the denominator. When I rationalize it, I get 8 roots of 3 over 3. When I double that for my hypotenuse, that's my 16 roots of 3 over 3. D is the easy one. 7, 7, 7 roots of 2. Everybody okay with that? All right. So I asked you to talk about why can't you solve for the height of the flagpole in this diagram. And I was trying to eavesdrop on your conversations, but I'm not sure I heard much of your conversation. What do you think? Talk to me. I'm going to tell you now, you can't solve for it. Nora's going to tell me why.
I have 2 reasons. One of them is it's not a special right triangle because that angle is 64, not 60. So you have no idea what the relationship between the sides are. And you can't solve via similarity because there is no similar triangle given to us. That's all I have.
But you could tell me this one too. Do I have enough to do Pythagoras? I've got 19 feet.
You only have one measure.
One measure. So Nora's got all 3. Whenever I'm using my math to solve for triangles, if I need Pythagoras, I need 2 side lengths and making sure it's a right triangle, and I'm in business. If I use my special right triangles, I need to know it's 30, 60, 90 or 45, 45, 90. I can use my similarity ratios, but unless I have another triangle, I don't have that ability. So every tool I have in my toolbox, not fit in this story yet. And that's what today's lesson is all about. And I want to focus on this story that Nora talked about. If we had another triangle, if I had another triangle where I knew it was similar, where I knew it was a 64-degree triangle, where I knew this side value and this side value, then I could set up a story. If I had A and B, then I could say the relationship between A and B is going to be the same as the relationship between my 19 feet and my height that I'm looking for. But I don't have this story yet. So here's what I want to do. We're going to explore a little bit more about ratios, and you're going to write these two ratios for each of these 4 triangles above. So your first ratio that you're going to write is going to be your short leg compared to your hypotenuse. So I'm going to go to triangle A. Here's triangle A. My short leg is 8. My hypotenuse is 16. So I'm going to write 8 over 16. My second ratio that I'm going to write is long leg compared to hypotenuse. When I go back to triangle A, my long leg is 8 roots of 3. My hypotenuse is 16. So I have 8 roots of 3 compared to 16. Would you please, with your group mates, write each of these 2 ratios for B and C and D? And you mark it, set, go. Talk it out. So check your work with mine and look at each of the 4 triangles. Look at each of the 4 triangles, and would you please make sure that you have all of the ratios written down?
She's gonna be me. Yay. Yeah.
Long leg to hypotenuse.
Yeah.
Long leg is 8.
In general, what are we
Hypotenuse is,
That's
oh, did I mess that one up? Long leg to hypotenuse. Did I look at it wrong? Oh, because I have to, this is just long leg to hypotenuse. This is just 8, right? Is that one better? Long leg to hypotenuse, right, Tanner? God, you can put a Smarty up. Make sure you have this one. Don't copy my work down. All right. So here's the deal. When I used to take my kids grocery shopping, they were big yogurt eaters. And they liked all kinds of yogurt, whether it was Dannon or Yoplait or Chobani, or they liked all the yogurt. So what I did every time was we got into the grocery store, everybody liked their kinds. Some people like the fruity, some people like the whatever. So we bought whatever yogurt was on sale. So I would send my kids over to the yogurt aisle with a basket, and I'm like, you guys go take care of the yogurt. So they would go and they would kind of fight over it because, you know, I get to carry the basket. No, you got to carry. So they get there and they would look at the yogurt aisle, and I had trained them to look at the little tags on the shelves that talk to me how much of the yogurt is per ounce. And those are called unit ratios. Do you know what I'm talking about, the unit ratios at the grocery store? Next time you're at the grocery store, take a look, because not only did I want the yogurt that was on sale, I wanted the one that was the cheapest per ounce. So they had to look at the little tags, and then once they figured out which brand was on sale or which brand was the cheapest per ounce, that's what they were able to buy, whatever they wanted to. They'd come back to me with a basket full of whatever they liked. Hopefully I had covered enough aisles without them that grocery shopping was tolerable, right? But what they were looking for was the unit rate. How much per 1 ounce? Because by dividing out, then we were able to have some kind of comparison regardless of how big they were, or whether they were on sale, or what they cost, or whether it was the cost per 6-pack or 8-pack. Whatever, I wanted the cheapest per ounce. So what we're going to do is we're going to turn each of these ratios into what's called a unit ratio, and our unit ratio is going to be that value compared to 1. And we do that by dividing on our calculator. So take your calculator with me, please. And if it's something easy like 8 divided by 16, no one's surprised that that's 0.5. This one's a little bit harder. 8 times the square root of 3. divide by 16. Sometimes I like to enter in between to make sure that I'm talking about exactly what I want. Your calculator knows the order of operations, so I want you actually pressing these buttons to make sure that you are following the same order of operations. So if you don't have a calculator, get one. And would you and your group mates please agree on all of these unit ratios? Go. So I need you pressing the calculator buttons because you need to make sure that you understand how and where I got each of these numbers. And the interesting thing is I want you looking at these patterns.
You know that math.
I want you seeing these decimals, and I went ahead and I took them out to 4 decimal places. So 4 decimal places is my tenths, hundredths, thousandths, 10,000ths, which means you got to look at your 100,000 and round. So when you divide each of these, you get a decimal value compared to 1. So just like that yogurt comparison, that decimal you're looking at, you're finding the cheapest per ounce. This is what you're finding per 1. Here's an interesting story. All of these decimal values for our 30, 60, 90 and our 45, 45, 90, do you see how they're the same? B and D are both 45, 45, 90 triangles. Do you see, even though I have different values, they have the same unit ratio? 45, 45, 90, they're similar. Do you see that A and C are both 30, 60, 90 triangles? Different numerical values, but same ratios. So they're similar. So this is where the mathematicians started thinking, and they're like, oh snap, do you see what just happened? And I imagine conversations between the mathematicians where the guy's like, no, what do you see? And they're like, do you see this? Imagine that one guy, super excited, the other guy like, I'm not following you. Tell me more. Every single 30, 60, 90 triangle has the same unit ratio. What? Every single 45, 45, 90 triangle has the same unit ratio. What? So you're asking yourself, what's the so what, now what? This dude's like, hey, I wonder if there's a unit ratio for every 64-degree right triangle. Because every 64-degree right triangle is going to be similar to every other 64-degree right triangle because they have angle-angle similarity. So they're like, wait, could we really do this? Could we make a 64-degree right triangle? Could we measure the sides? Could we divide them and come up with ratios? And the guy's like, yeah. And if we do it for the 64s, we should do it for the 63s and the 62s and the 61s and the 60s and the 59s, the 58s and the 57s. And someone's like, wait a minute, we should do it for the 65, 66, 67, 68, 69s. And they're like, yep, we got a lot of work to do. Flip your warm up over.
That's what the sign is? That's what cosine is?
Cosine and sine.
Here is the fruits of their labor. They measured and divided and gave us all these values. So here's the thing, they lived a long time ago and they spoke in different kinds of dialects and conversations, and they had nicknames and things that we're not to understand. So they called these ratios sine, cosine, and tangent. Say them, sine, cosine, and tangent. That's what they named the ratios. So they compared the sides of the triangle. Can you do me a favor? Come on over to your 64-degree triangle. That means that these 3 ratios are your unit ratios to help you with the triangle. So then they're like, wait a minute, we got to get organized. We need to get organized. So here's how they got organized. They drew their triangle, and they were Greek, so they used a Greek alphabet letter. That is theta. Theta is a circle with a little squiggly line through it. That's a part of the Greek alphabet. And they said, hey, whatever angle measurement we're talking about, let's call it theta. And they're like, okay. And they said, don't forget, this only works with right triangles. They're like, okay, we got that. Then they said, let's go ahead. And again, we're not creative when we name things in mathematics. You know that. Let's say that the side opposite of theta is called the opposite.
Wow, guys.
And he's like, ooh, I like where you're going with this. And they're like, what about this other side? He's like, okay, this side that's attached to theta, let's go ahead and call him the adjacent side. It's like, okay, I see where you're going with this. And they're like, what about that third side? What do you want to call him? They're like, he always has the same name. We call him the same thing all the time because he's always opposite the right angle. What's he called? Hypotenuse. So they had these three sides of the right triangle. They're like, I have my opposite, my adjacent, my hypotenuse. They're like, okay, what comparisons do you want to make? And when we go through these, we can come up with 6 different ratios. We can come up with opposite to hypotenuse, hypotenuse to opposite, adjacent to hypotenuse, hypotenuse to adjacent, adjacent to opposite, opposite to adjacent. They're like, that's too many. Let's just call 3 first and let them learn 3 when they're in geometry, and then they can learn the other 3 when they're in pre-calculus. And they're like, oh, that's a good idea. Let's limit it to 3. So the sine is going to be the relationship of your opposite compared to your hypotenuse. Your cosine is going to be the relationship of your adjacent to your hypotenuse. Your tangent is going to be the relationship of your opposite compared to your adjacent. So they named those 3 trig ratios wackadoo crazy values. But how they got them makes total sense. All right, let's go back to our flagpole problem. I know that when I compare my opposite to my hypotenuse, my ratio is this. My adjacent to my hypotenuse is this. My tangent to my opposite to my adjacent is this. Let's go back and see what we have. If 64 degrees is our theta, do you see that B is our opposite? Do you see that A is our adjacent? So the tangent of 64 degrees, which is equal to our opposite compared to our adjacent, is going to be the similar value to help me solve for the height of my flagpole.
I'm done.
So they're telling me that I can get this value, 2.503. 2.5030. Do I have it right? 2.0503. 0503. We like that better. That's going to be equal to our opposite, which we don't know, and our adjacent, which we know. If we put this over 1, that gives us a proportion that we can solve. It's crazy, but it's a way that they gave us so that we can solve trig ratios. Take a minute and digest with your group. Here we go. We're going to go back a little bit and define some things officially for your notes. Trigonometric ratios. Say that word for me. Trigonometric. I want to hear everybody say it. Trigonometric. Yeah, trigonometric. Trigonometric ratios. And it's funny, we can understand different things that we're talking about there because it references unit ratios. So you're going to think about the yogurt for corresponding sides of similar right triangles. So it only happens in right triangles, and the triangles are similar because we understand them through angle-angle similarity. Angle-angle similarity, because once I have the degree measure, it's a right triangle. Those are my two angles. When we talk about a unit ratio, that's going to be a ratio compared to 1. Now, what's interesting is we abbreviate sine, cosine, and tangent as this way. Please don't call it sin. Please don't. It's sine. Please don't call it cos. It's cosine. And when we talk about tangent, that's the one we're okay with you calling it tan. But for the most part, we like sine, cosine, and tangent. Those are just the silly names that they gave to each of these 3 ratios that we can make. My opposite compared to my hypotenuse, my adjacent compared to my hypotenuse, my opposite compared to my adjacent. That sine is my ratio, cosine is my ratio, tangent is my ratio. It just tells me what the story is. At the top of every paper that I work on, you'll see me write SOHCAHTOA because that is my little trick to remember that the sine is the opposite over the hypotenuse, cosine adjacent to hypotenuse, and tangent is the opposite to the adjacent. Sometimes you'll see people abbreviate it or call it SOHCAHTOA. And if you go home and Google that, there's all kinds of crazy stories. Some people have made it into some Indian tribe SOHCAHTOA, and the chief and the hypotenuse, and they come up with this story, and that's kind of silly. And they'll tell you SOHCAHTOA is how you remember it. It's a mnemonic, same as like PEMDAS or other things that you use to remember things. I stink at that because for me, I always struggled with spelling. So I can recall as a young geometry student, pencil poised at the top of my paper trying to remember how to spell so, S-O-A. S-O-H, S-O-O, so, okay. So SOHCAHTOA never worked for me. What I use to remember the ratios is some old hippie caught another hippie tripping on acid. Works for me. Some old hippie caught another hippie. So whatever works for you, you're welcome to use. Here's the most important part. You need to understand, first of all, which angle you're talking about. Because if your angle theta is angle A, your opposite side, picture somebody sitting across from you at the dinner table. That's your opposite. You can right now lock eyes with the person, everybody but Nora. I'll come stand here for Nora. Lock eyes with the person opposite you. Now you can lock eyes with the person that's adjacent to you. That's somebody that's adjacent.
Who's there? Actually exists.
We're also the other one.
Adjacent, we can talk about whether you are attached.
The hypotenuse.
Your hypotenuse is always Your hypotenuse is always opposite. Your hypotenuse is always going to be opposite your right angle. All right, so let's come down here. And when we talk about writing these ratios, we've got angle P. So we'll talk about angle P here. And we'll give P our theta. We'll label our theta so I know which one I'm talking about. And I can write 3 ratios about the side lengths of angle P. I can talk about the side that's opposite it, the side that's adjacent to it, and the hypotenuse. So if I want to know my sine value, my sine represents my opposite value, which is 15, compared to my hypotenuse, which is 17. My cosine value is going to be the attached side compared to the hypotenuse. And my tangent is going to be my opposite side compared to my adjacent. That's what governs the ratios that I write. Now these are 3 of the 6 possible ratios. The other 6 ratios are all the reciprocals of these, and like I said, you'll learn them in pre-calculus.
In reference to this angle.
I can't hear you.
The symbol you put in the triangle, where did you say it was from?
That's theta. It's part of the Greek alphabet. Alpha, beta, gamma, delta, epsilon, theta, eta, theta. Iota, kappa, lambda, mu, psi, omicron, pi, rho. Sigma, tau, epsilon, psi, pi, phi. You're the last one? Omega. Greek alphabet. Yeah.
How do you know where to place your finger?
It tells me. I'm talking about angle P, so I put my theta in P. Great question, Cole, because Cole's like, wait a minute, so are you saying then for angle Q, that becomes my theta? And I say, yes, sir. And he's like, wait, snap. That means that my opposite is now 8, so my sine is not the same value, even though it's the same triangle. I'm like, you are exactly right, because the angle P's and Q's are complementary, which means your cosine is going to be your adjacent compared to your hypotenuse, and your tangent is your opposite over your adjacent. Will you please use your calculator and rewrite each of these 3 ratios as a unit ratio, meaning as a decimal? Pretend like you're telling me how much the yogurt is. Go. So as you're doing these, you'll notice a couple things. First of all, the cosine of Q is the same as the sine of P. Ah, so complementary angles are going to have that cool relationship between sine and cosine. And you're like, I wonder if that's really true. So I'm like, I don't know. Check out the back of your warm-up. Look at the back of your warm-up. Find 2 complementary angles, 1 and 89. Check out their sine and cosine values. Check out their sine and cosine values. Are they opposites? They are, aren't they? So those sine and cosine values that we have, those sine and cosine values, have a pretty cool relationship. When you look at these decimal values, my friends, those are the values that the gods gave us. The Greek math gods said, here you go. Here's all of the unit ratios of all of the angles. Sine, cosine, and tangent. So very cool. All right, here we go. Here is a review of how we solved for our flagpole. If we knew the unit ratio of the opposite side to the adjacent of a 64-degree angle and the right triangle was that, could you solve for the height of the flagpole? And what was interesting is we didn't make that up. That 64-degree angle does have a tangent value of 2.0503. So now if I know that this unit ratio exists, I can use it and cross products to solve for x. My x value is going to be equal to 19 times that 2.0503, and that value is the tangent of 64 degrees. And that's how I get 19 times 2.0503, and that gives me my 38.96 foot high flagpole. Mathematicians love flagpoles. All right, so we're going to be using these ratios. So here's what I want you to do. A couple of things that you want to pay attention to. Owen, are you with me? I want to make sure that you know that this is a thing. The sine of 23 is a thing. It's not 23. It's 23 degrees, and it's the ratio of that 23-degree angle. So he stays kind of bundled up together until we either get that value or somebody gives it to us. We can set him over 1. We can then use cross products to solve. X times 1 is x, and 15 times this sine value of 23. And that sine value of 23 is a unit ratio that somebody's got to give us. That's a unit ratio that somebody's got to give us. So let's take a look at cosine. Ready? Cosine, bundle them up. Cross products. My W is equal to 5 times that cosine ratio, that unit ratio of a 74-degree angle. Let's talk about tangent. Bundle them up. Put them over 1. Cross products. Y times my tangent of 60 degrees is going to be equal to 3. This one's a little trickier. It's not working out as well. So in order to solve for y, I'm going to have to divide by my tangent of 60 degrees. So I know my y is going to be equal to 3 divided by my tangent of 60 degrees. Those sine, cosine, and tangent values are constants. They're fixed. Flip over on the back and you can see every single one of those values. Flip over on the back. Find the sine of a 23-degree angle. Talk to your group mates. Where's the sine of a 23-degree angle? Put your finger on it. Make sure your group mates are with you. It comes from that chart. If this is too complicated, let me know. Close it.
45 and 90 not on for a reason, or did they just like cut off when the kids was
They are special so there's no 90. Because it won't be there. And the 45 is your
But I just wasn't sure if I was
You can add it. You can add it.
you know what we actually calculated it to.
Right?
So it's 707.
Also, just 0.5.
So Nora asked a great question. She's looking down here and she's like, wait, I don't see a 45-degree angle. But you can add it because you figured it out. You figured it out because your sine and your cosine are going to be the same, 0.7071, 0.7071 because it's isosceles. Here's the cool part, your tangent's 1 because it's opposite over adjacent, and in an isosceles triangle, don't they have the same value? So you can add that to your chart. But there's an easier way. Calculator. Would you all pick up your calculator? Would you all turn it on? Would you all do second mem 712? Second mem 712 clears your calculator and wipes out whatever the person before you was using. Do you need to see it one more time?
Yeah.
Second mem is the plus sign. If you choose 7, it's a reset. 1 is all RAM. 2 reset. You know you did it right if you got that screen. Are you with me?
Yeah.
Would you please hit this button here that says mode?
Scary.
Mode. So here's the story. Here's the story about mode. If you don't remember to push this button, every single answer you get will be wrong. Because this calculator is set up with the default of radians. Do you see the word radians? Radians are how a circle is measured in terms of pi. If you look over behind Krista on my calculus posters, that's the unit circle, and the unit circle is measured in pi, and that is radians. When you get to pre-calculus, you'll learn all about that. For now, we're working in degrees. So what you need to do is arrow down and over, arrow down 2 and over 1 until the word degree is highlighted, and press enter so it changes. So you're going to go down 2 over 1, and you'll notice if you press enter, then now my degree is highlighted and not my radians. Are you ready for something very cool? Just hit second quit to enter, to exit. Now I told you we could go get the sine of 23 from our chart, but the mathematicians took the time to put all of these values in the calculator. So my x is equal to 15 times, see these buttons here? Sine, cosine, tangent. 15 times the sine of 23.
Uh-oh.
Make sure we match. X is equal to,
Mine says sine. Where's the normal
You hit
sine?
second.
don't
It's just
hit
a normal
second,
thing. I'm sick.
don't hit second. Play with it till you get it.
23.
Yeah.
Math.
Play with it
And
till you
that's
get it.
what I got. Whoa, I got one off.
So if you're curious if the calculator's right, you can just ask the calculator, hey, what's the sine of 23? And if you go to your chart, the sine of 23, it has it as 0.3907. 0.3907. So if you like the chart and you want to get the sine of 23 from your chart, rock on. Most kids I know prefer the calculator. Let's talk about B. If W is equal to 5 times the cosine of 74, go ahead and type in 5 times the cosine of 74. And you should get a value of ready? Y is equal to 3 divided by the tangent of 60. Y is equal to 1.7321.
You got it. And then
Would you please turn to your group mates and explain where these numbers inside the calculator came from on your market set talk?
the shorter way and the shorter way.
All right, come back.
Shorter and then you do it.
So we're feeling okay, fellas. So we go this way, and we solve these, no problem. So we're feeling good about this, and then we hit the next line, and we're like, wait, this time my x, my theta, my unknown is a part of my trig function. So here I'm solving for a triangle side. And then I get down to this part and I realize I have two sides of my triangle. Here I'm solving for my unknown angle. So what this means is there's a triangle out there that's a right triangle, and there's some x angle measurement that has an 8 to 15 story between the opposite and the hypotenuse, and I know that's the ratio because they said sine. So I need to know which angle has that ratio. So if you go back to your calculator, you'll notice above your sine, cosine, and tangent buttons are the little inverse. See how it's to the -1? So you're going to be using the inverse of the sine and figuring out that the angle that has this sine. Now we can do this on the chart also. Go ahead and divide 8 divided by 15. Do you see that 0.53333333? If we're looking at that sine, do you see 0.533333 would be in between these? So it'd be somewhere in between. Now our rule of thumb was we're always going to round to the nearest whole degree. So then you would have to decide, is that closer to 52 or closer to 50 or to a 32 or a 33 degree angle? The calculator can answer that question for us. Hit your second function, hit your sine, and do your ratio, 8 divided by 15. You're asking your calculator here which angle has this story between the opposite and hypotenuse of the triangle. Give me the angle whose sine is 8/15, and it'll tell you that is a 32 degree angle. So for these where my unknown value is a part of my trig function, I'm solving for that angle. So I'm asking the calculator here, which angle has the cosine of 13 divided by 17? tell me an angle in a triangle whose adjacent and hypotenuse has this ratio, and you should get the inverse cosine of 13/17 is equal to theta. So theta is equal to 40 degrees. And again, we're going to round to our nearest whole degree. Talk to your partners about solving this one. Turn and talk. Go.
So there can't be.
How we do it? I heard somebody over there go, did you get 70? Feels good when you figure it out. All right, here's the notes that explain what we've been doing. We're going to work on solving right triangles. And when we solve right triangles, we're going to use trigonometric ratios to solve for the missing sides and angles. When I ask you to come back to the starred section, this is the one I'm talking about. Because we've got a lot of tools in our toolbox, and it's important to know which ones I'm using. If I have a right triangle, and I got to tell you something, that is the most important part. None of this noise works without a right triangle. So I got to start with a right triangle. If I have another angle and a side, I'm going to use my triangle sum theorem to find the other angle. I'm going to use my trig ratio to find my missing sides. If I'm given two sides, I'm going to use Pythagoras to find my third side and my trig ratios to find the angles. When we talk about and when we're asked to solve a right triangle, they're asking us to find 3 angles and 3 side lengths. That's what it means to solve a right triangle. If somebody says, hey, will you solve this triangle? They're asking you, I need you to identify every single angle and every single side. Here's the good news. We already have the right angle and at least 2 other pieces of information. All right. So if you look at your note page that I gave you, that I passed out, go ahead and write on the top of it, 7-3, page 2. So this is the calculator notes, making sure that you remember. If you want to know where to find your ratios, you can use the chart. You can use the chart or you can use your graphing calculator. You want to make sure that you know your mode and you change it to degree. If you are looking for the angle, you're using the blue second function button. And you're using that angle whose sine or cosine is to figure it out. Last year when we were online, a lot of Desmos users. Last year when we were online, a lot of folks were Desmos users. So you need to go to your wrench key. And when you go to your wrench key, you need to make sure that you switch it from radians to degrees. And then you need to go to your functions and you need to choose trig to find the sine, cosine, and tangent. All right. When they ask us to solve a right triangle, they're asking us to find 3 angle measures and 3 side measures. So when we talk about our angles for this first triangle, I know I have a 90-degree angle. I know I have a 42-degree angle. Can you help me solve for angle T super fast? What is T? Yeah. So this is my given, this is my given, this is my first angle that I'm asked to solve for. My triangle sum theorem helps me out, no big deal. Let's talk about our sides. I have one side at 15. Now, you have a choice on whether you want to use 48 degrees as your theta or 42 degrees as your theta. Do you know why I always choose 42? It's given. Anybody ever do stupid math and mess up on subtracting and get points off because you didn't do the basic math right? Has that ever happened to you? So if I have a choice of using a value that I've calculated or one that's given, this is the one I'm going to use, and I'm going to mark that as my theta. Now let's talk about, with this theta measure, my opposite is side U. My adjacent is V. And 15 represents what? So it's going to take me 2 trig ratios to solve for U and V. So I'm going to review my sine is equal to my opposite divided by my hypotenuse, some old hippie. My cosine is my adjacent divided by my hypotenuse, caught another hippie. My tangent, opposite divided by my adjacent on apples. So when I go to solve, let's do U first. I know that the sine of 42 is going to be equal to my side opposite, which is U, over my hypotenuse, which is 15. I'm going to put this over 1. And I'm going to say that my U is equal to 15 times the sine of 42. You have to show me that work so that I know you've plugged the right values into your calculator. 15 times the sine of 42. That's side length, and we're going to round to 2 decimal places, 10.04. Now let's go ahead and solve for V. Now I'm going to solve for V. I have my adjacent and my hypotenuse. So I'm going to use my cosine for this one. My cosine of 42 is equal to my side length of V over my hypotenuse. So I know that my V is equal to 15 times the cosine of 42. Fifteen times the cosine of 42. My V is equal to 11.15. 3 sides, 3 angles when I solve a right triangle. 3 pieces of information are already given to me, 2 angles and a side. I use my trig ratios to solve for these sides and this angle. Let's do another. You ready? Stay with me. Yeah. Pythagoras?
Yeah.
Sure. Because once I have 15 and 10.04, if you want to do 10.04 squared plus v squared is equal to 15 squared? Yes, absolutely. Can you stop throwing it back and forth? Just stop. It's not the first time. All right, let's talk about solving this triangle. What's the measure of angle B? Come on. 25, I love it. Which one do you want to make your theta? Me too. I'm always going to go with what's given to me first. I have my opposite. There he is. I need to find my hypotenuse and my adjacent. So because I have my opposite and I'm looking for my adjacent and my hypotenuse, it looks like I'm going to be using sine and tangent. So let's go ahead. Do you want to solve for x or y first? Pick. X, I heard. What is x? My hypotenuse. So I know that my sine of my angle is equal to my opposite over my hypotenuse. So the sine of 65 degrees is going to be equal to my opposite, which is 8, compared to my hypotenuse, which is my x. Cross products has me at 8 is equal to x times the sine of 65. Now I bundle that up and I keep it all together because I can go ahead and divide it, and it's easier working with the sine of 65 than all those decimal values. So I know that x is equal to 8 divided by the sine of 65. This is a trigonometric value. You can go to the chart and get those digits, or you can go to your calculator and you can say, hey calculator, what is 8 divided by the sine of 65? So that means that my x has a value of 8.83. We're going to round to 2 decimal places for side lengths. There's my x value. Now it's time to solve for y. When I want to solve for y, that's my adjacent. So my tangent of 65 is going to be equal to my opposite over that y value. And then you can solve.